So hello everyone, I'm really pleased to have you guys here. The presentation is titled Understanding Distributed Calculi in Haskell. My name is Pawel Szulc. I work for a company Pyrofx, where we do a blockchain, which is called RHO-lang in Scala. And if you've seen the closing keynote for the first day, Mike Steyer is actually the CTO of the company where I work for right now. You might be wondering, okay, so you do Haskell for a living and the presentation is in, so you do Scala for a living and the presentation is Haskell. What's the point? Where there were multiple of reasons, but I felt like LambdaConf, the main Haskell developers here, so why not do it in Haskell? So yeah, let's talk about distributed process. Distributed process is something that some people actually known as a cloud Haskell. It's a library that allows you to write programs a little bit like RHO-lang style. Hopefully there are no RHO-lang developers here because I will not answer the questions differences between those two. Because there are numerous differences and distributed process will be not ever as powerful as RHO-lang is, but we can get actually a lot of cool things from RHO-lang in writing Haskell code. It was highly influenced by this paper, but with some changes from RHO-lang people. Now, just to give you an overview of what that is, there we go. Just to give you an overview of what that is, in the distributed process, you have a data type called process. It's a monad, so it gives you this ability to reason about distributed computation, about process running somewhere on your node. Each process gets an ID, process ID, and we have a method like, for example, some function like, for example, send, which takes the process ID, takes something of value A, and gives us back a process of unit. Equivalent, we have a method expect, which just awaits and waits for a value and gives that value close over process. And both of those values has to be serializable. So just to show a very quick example, imagine that we have a node master, and that master spawns two subnodes, subprocesses, ping and pong, and then master will send a message in it where it hold its own master ID, and it also will hold a pong ID, and it will send a message to ping. Ping will be like, okay, fine, thank you. It will send a message ping to pong. Pong will, guess what? Send pong back, and then ping will, and then it will die. Ping will send a message done, and it will die, and the master will die, and the program ends. Pretty straightforward example, right? And this is how we would write it in using distributed process library. So there would be a bunch of inputs that we need, some extensions to the language as well, but let's just focus on what's important. Here I have my very simple data type, which I call protocol, which are basically the messages that you've seen just a moment ago. Initialization, ping, pong, and done. Then master is a process that first, when it's initialized, it gets its own ID. It spawns two local ping and pong processes, not yet defined, and then it sends a ping message, a message in it to ping ID, so to that process, and then it waits. So expect is waiting for some message to resolve. It pattern will pattern match on the kind of message it's hoping to get, and it's actually done. So ping itself is pretty similar. It expects, first of all, it waits for the end message. Once it gets it, it will fetch its own ID, send a message pong with his bit to a pong process, then expects for pong message back and sends done to master. And as you can imagine, a pong process will be pretty much similar. So it waits for ping and immediately sends pong back. And the way you execute a program is you create a transport layer. The library is pretty well designed, and I'm not going to go into details of how that is because that's not the distributed process tutorial, but it's pretty straightforward to just instantiate a running node and just run your program in it. And there's an additional helper method here, a logit, that takes a string and returns as a process of unit, just logs some stuff to the console. So I basically do that to the processes that we've seen so far. I add some log messages here to ping, to pong, and to master as well. Any questions so far? No, good. Okay.
I do have a very small one. It's just because I don't know Haskell very well. What happens if expect doesn't return done, or is that the only thing it can return?
Just wait for it. Like we have like 30 more minutes, so we'll get to that. So we build it, we run it, it works. It basically works as expected, and we feel like a boss. Actually, we're not, because it's a trap. And the trap is, this is fairly easy program, but there are already some issues in it. First of all, when I first approached this library, I was thinking, oh, this is so cool, writing distributed process in Haskell, so I get all the type safety from Haskell, while at the same time I can actually write a distributed system. Well, not exactly with this API. So for example, expect waits for a process of A, where we pattern match on done, what it means that you can pretty much, like in Akka and Scala, you can send any kind of message, and it will just keep on, the mailbox will keep on receiving those kinds of messages, but it will eventually just blow up your stack, and the whole thing will explode, and you will not have a good time. Secondly, it's very easy to send messages which don't adhere to protocol, and you will not get any information from the compiler back. You send a wrong message, which is not adhering to the protocol, and the compiler will be like, yeah, fine, whatever. And you will run it, and things will not go correctly, and the program will not behave as you would like for it to behave, and you be having a bad time. I was actually implementing the Lampert's logical clocks using this library, and the cool thing, it was really straightforward to implement that paper, but the error exactly was in types. I've sent a message. Yes?
Sorry, paper title again?
It's like if you Google logical clocks, virtual clocks, and something in Lampert, you will find a paper. Yeah. It's it's the only Lampert paper that you can actually implement from just reading that paper, not other papers explaining what Lampert actually meant. The implementation, if you're interested, is on my GitHub. I can later on show you. It's pretty. You just go paragraph by paragraph and just implement everything as it is, and it just magically works. But it didn't for the first time. And the reason why it didn't was basically that at some point I sent something which I wasn't supposed to. I just forgot to wrap one type over the other type, and compiler was happy, and but my program wasn't. So now the question was, could I get some sort of formalism that I could reason about my programs which are distributed? Obviously, we have Lambda calculus. Pretty much, I guess everybody is familiar with Lambda calculus, but I will quickly go through it anyways. So Lambda calculus has this three terms. Sorry, like you can either have a variable, you can have an abstraction which represents sort of a function that takes this argument x and does something in m, or you can apply an argument to application. You apply an n to an m. Within the Lambda calculus, we obviously have something. So the x variable here is, we call it called bound variable. So what that means is that those two Lambda expressions are equivalent. We talk about alpha equivalence. So because if we look at those two, pretty much they differ only on x and z and y and w. Other than that, they are equivalent. So we are saying there is something we call alpha conversion, where we say we can go from lambda x m to lambda y m, and the only thing that we have to do is that within m we have to replace all occurrences of x with y, and then those two will be equivalent. So far, so good? Yes. Okay. So, and there's also a concept of free variable. So a y here is a free variable, so it's not being represented before this dot here. And last thing that we have to remember for Lambda calculus, which will be pretty much important in just a second, because we will look at equivalence to other calculuses I'm going to talk about, is a beta reduction. So beta reduction is nothing else than just applying argument to a function, or you can think of it as a single computation step. So you have your Lambda calculus, and you can now try just to run it. Try to be a computer that just executes it and just go step after step. So beta reduction looks pretty straightforward. If I have an application that looks like this, so this is a Lambda expression, this is another Lambda expression, this is exactly equivalent to just n, where all the x's within m all the x's were replaced with an m. So that's how we apply arguments to and then we sort of like reduce the Lambda expression until it's not reducible anymore. So just a very simple example here. First of all, I will, in the first step I take z and I apply it to, so I remove x here, I take z and replace every occurrences of it. It doesn't exist. Sorry, x is not being used. Sorry, x is being used here, so that z becomes that z, and I do the same step one more time, and I get z back. at the end, and the expression is reduced, and I cannot reduce anymore. Okay, so the question might be, is that it? Is that a whole Lambda calculus? Where are my types, right? Around Booleans and things like that, numbers and whatnot. Like, obviously, this is a typed Lambda calculus, but on top of that language, other things will build on top of that. So we have different encodings, church encodings and Boolean encodings. But really quickly, you know, a simple encoding would be that we don't have something like a multi-argument functions in Lambda calculus, right? Something like that doesn't exist. But we can quickly think that we could create like a syntactic sugar for our Lambda calculus, where a Lambda that takes 2 arguments is actually a Lambda expression that takes 1 argument and returns a Lambda expression that takes another argument and then continues with M. We know that by name, right? What's the name? Yes, it actually was invented by Schönwinkel. Schönwinkel wrote a paper like 50 years later. I think Curry read it for like, this is awesome, and just expand the idea. But I guess it's a right, like, it would be really hard to say in Haskell all functions are Schönwinkel by default. Let's stay with Curry. Anyway, Boolean values can be encoded. Church numbers, like, it's not really about Lambda calculus, but I'm just saying this presentation isn't about a Lambda calculus, but I'm saying it's possible. Now, the question is there a calculus, or could I use Lambda calculus for distributed computing? And the answer is not really. The problem that we have is Lambda calculus is sort of more designed for sequential computation, while distributed computation can happen in parallel. Now, a nice feature about Lambda calculus that it's really easy to reason about Lambda calculus, because you can only have to think in terms, oh, I have this input and I expect this output, and that's all there is. The problem with distributed processes is that they differ even if they look alike. So you might have a formalism that the 2 processes will look the same, but for example, one of them doesn't handle errors and the other one does. You might have formalism when 2 systems look the same, but one system is running on a single processor where you have different cores that communicate between each other through shared memory, while at the same time you have another system where processes actually communicate over network, sending messages. So there will be no single calculator, there will be no single formalism for distributed process. It's sort of like depends of what you deal with and what kind of system you're talking about, what are your assumptions for the system, and so on and so forth. The system that we'll be covering in this presentation are systems where processes exchange information through sending messages. The first 2 formalisms that I know about were sort of published and researched in the beginning of the 80s. One is by Robin Milner, because of communication systems, and the other was by tinier, communicating sequential processes. And both papers pretty much describe a very similar approach to talk about distributed systems. However, a few years later, Robin Milner expanded the ideas from this paper, and he came up with something which we now call pi calculus. So pi calculus is basically just a model to reason about concurring system. Within that model, we have something that we call a process, and we also have messages, and those messages are being exchanged between processes through channels. That's really what it is. Okay, so far so good with the definition. Cool. So the thing is, the processes exchange those messages. Important thing is the communication is synchronous. It's sequential. You can reason about determinism. You can talk about replication, creation of channels, and all that is available within that formalism. So this is the syntax, and it looks scary, but it really isn't. So we have ability. Okay, let's just go one after the other. So first of all, you can create a process, 0 process. It's the simplest process that just does nothing. 0 is I'm done. I started and I'm done. That's it. The other process would be something which we call input prefix. What it means is that this process awaits on channel X for message Y, and once the message arrives, it continues with whatever is in P. Okay? The next one would be the output prefix. It's the other way around. What this process is doing is basically sending a message Y over a channel X. So that underscore in the paper is here. I just don't know how to use LaTeX, so I pretty much just said underscore. And but that's the only difference in the original syntax. Okay. So yeah, so now you have ability to send message through channel X and retrieve that message at the same channel. So now we could maybe write a simple program that we send hello, we spawn a process, we send hello to itself over that channel, and we receive that message. So it could be something like this. I send a message hello over channel X, and then on that same channel I expect some message MSG, and then I finish my computation. It could be something like that. So I have my process P, there's a channel X over which I send the message hello, and message hello goes back, and the calculation is done. Unfortunately, it's quite not like that. The problem is that everything within this formalism, in this calculus, is sequential, is synchronous. So what it means is that this is sort of counterintuitive to anybody who work on any distributed system which are asynchronous by nature, because you think you send and forget, right? You send a message and you're done. In this Calculi, it's assumed that this waits for the message to arrive from channel X. That is pretty obvious, and just waits here for that message. But also, this part of code waits until the message is actually retrieved by somebody. So it only continues with further calculations if somebody is reading that message. But the only process here that can read that message is the same process. So it's stuck here and it will just not go on. So we need something else. And that's why we get a parallel composition. So P parallel to Q means we have a process which spawns internally two subprocesses, P and Q, and those processes run in parallel. There's also something called restriction. So that Greek letter here is being pronounced as ni. So if is anybody watching Monty Python, you know how to pronounce it. And it basically means I will create a new channel for you, new channel X, that will be unique for that process P. So in other words, we can think that this restriction binds our argument to X. So just to give you an example, imagine that we have some process P that sends a message X over some channel Y, and now if we have Q, which is ni X P, it pretty much means this exactly. So you can see right now that the name X is bound here. What is super important, which I just remember I forgot to tell you, is that in Pi calculus, the message can be the channel itself. So I can have a channel, and I can send that channel over some other channel to somebody else. So we can have communication here, right, over some channel, but I can take that channel over which we communicate, and I can send that to somebody else, and he will have ability to see the messages that we exchange. So now, and we sort of see that those two are equivalent the same way how in Lambda calculus we have alpha equivalence on Lambda expressions. Do you guys see the correspondence here? It's easy to reason about Pi calculus if you try to look for correspondence in Lambda calculus itself. All right, and with those 5, we can actually create a small program. So here we have a process P that sends a message hello over X. The other one, Q, expects a message MSG on X. And we have R, which runs in parallel. So it spawns a new channel X and then push P and Q to run in parallel. So we can forget about 0. It's like a synthetic sugar because 0 doesn't do anything. And now a little visualization with the magic of PowerPoint. We have a process R. It spawns two processes P and Q. They have a unique channel X over which P sends a message hello. That message is being received on Q as MSG. P ends its calculation, Q ends its calculation, and so R, and the calculation is over. The last bit, replication, it pretty much means that in the formalism, there might be multiple copies of P running in parallel. That's really what it means. So there is a concept also of a structural concurrence. It means that two processes are structurally concurrent if they are identical up to the structure. So it means they have They may have a different structure, but they behave the same. Those are the rules. So if I have a P and Q running in parallel, this pretty much means the same thing as running Q and P in parallel. If I have a process that has a process P and Q in parallel, and I run it parallelly to R, that is equivalent to having a P running in parallel to a process that has Q and R running as a subprocesses in parallel. And also, if I have a new channel X, which is unique to P and that runs in parallel to Q, that is equivalent to having P and Q running in parallel and having X unique for them. And also, this last one sort of explains how the replication works. If I have a exclamation mark P, it means P in parallel to the exclamation mark, and it can just expand infinitely. And the order of how you create your new channels doesn't really matter. So reduction rules. Reduction rules are, one more time, equivalent to what you would have in Lambda calculus as a beta reduction. So it is a computation step that you can do within that Calculi. So the first one is called communication. If I have two processes which run in parallel, while one process sends a message over channel X and the other process expects that some message on channel X, it is equivalent to having a P, to having P, so the continuation here, running in parallel to Q, where all occurrences of Z were exchanged with Y. So it's a simple communication. I've just sent Y here to somebody who's waiting for it, and basically we're waiting for message Z, so we just have to rename it, right? The same thing, if I have P running in parallel to R and P is reducible to Q, then P in parallel to R is reducible to Q running in parallel with R. It just means that it doesn't matter if the process runs in parallel to something else, I can still reduce it internally. And the last one is like if I have P that has a unique channel X and have a P reduces to Q, then this expression reduces to new X, ni X Q. So just having that new channel in front of your P doesn't stop you to reduce P even further. And the last one is called structural concurrence. It means if I have a process P and P is structurally concurrent with P prime and Q is structurally concurrent with P prime, and also I can reduce from P prime to Q prime, it means I can reduce from P to Q. So those are all the rules that are needed in this calculus to run reducing steps, to basically evaluate your program, your distributed program. So simple examples. Ping and pong, I have a ping that sends a ping and it expects a pong, and then there's another process that expects first ping and then sends pong back, and I run them in parallel. So here I run them in parallel, and you can pretty much see that over the same example here. Over the communication rule, I can eliminate those two first, and then I can eliminate with the same rule. I can eliminate those two, and that sort of ends the computation. Well, the question is, does it end the computation? So in the papers that I wrote, I actually couldn't find a rule that actually looked like that. In other calculus, like for example raw calculus, this rule is obviously stated in the paper. And in the PyCalculus papers, I actually couldn't find it. However, I found that when I was reading about PyCalculus on Wikipedia, I've actually found that on Wikipedia. And you know, think about Wikipedia. If it's on Wikipedia, it's true. So I call it Wikipedia equivalence. And let's go on with it. So P ends and then the calculation is over. Second example is here, the ability to send channel as messages. So I have two processes P and Q. And so what I do is with communication, I send Y. So you see here, the Y is actually a channel, which I can send over to another process. And then that channel can be used one more time as a communication element. So this right now, before that, Y was being a message. And then it was being sent to another process. And then that other process will use it to retrieve some messages from that previous process. So now the Y is being used as a channel here. And we will read this further and further, and that's basically it. Here we have two messages, ping and three processes, ping and pong twice, and if we try to run it, obviously we've seen that we could reduce either this pair or that pair. So depending which way we will go, we get a slightly different result, which is still sort of equivalent. But we can reduce that. If you guys don't mind, I'll just go quickly over slides because I really want to reach row calculus, but we might not get there. Even though I'm trying to be Anyman at this point. So ping pong. Oh, ping pong. If I run ping pong with replication, we can actually see that example. So as you remember, over the replication rule, exclamation mark p is p in parallel with exclamation p. So that means I can just expand it. Those will rule out themselves. But one more time, you can do it till the end of the world, and they will run forever. Now, nice thing about this calculus is the fact that you can reason about race conditions. So here we have a very simple process that runs 3 sub-processes, but you might see that there's one sub-process that waits on a channel X, while we have 2 different processes that try to send a message on that channel. And depending on which one will actually win the race condition, we might get 2 different results. So that's a very nice feature from this formalism, that we actually can reason about race conditions, and actually we can reason about whether our system might end up into different places. I will just skip by simulation. Okay, the benefits. I can reason about my computation. I can reason about my computation in the distributed system. I can reason about non-determinism, which is not always necessarily something I need to have, but it's nice to have it. I can reason about my structure. It's really good to describe protocols, and a formal framework to provide semantics for high-level language. Because it would be really nice if we could write an interpreter that would go from PyCalculus to something else, some other language that we are familiar with, and then we could sort of like reason about some distributed process that we have, write it down as a PyCalculus, and just get it running using our interpreter. So, back to distributed process. I lied. Distributed process actually has 2 different APIs. One is sort of this Haskell-like, which is sort of non-type safe and whatnot. The other one is pretty nice. They have actually a concept of a channel. So channel is a tuple that has a send port and receive port. And those are distinguished for a reason which we're going to see in a second. So we have a function that when we call it, it spawns for us a new channel, and that is closed over process. And then we have 2 equivalent methods. We can now send messages over channel, so we need a send port, so that first element from the tuple, and we can receive messages from the channel using that second element from the tuple. So that's fairly easy. We no longer see any processes IDs. We just spawn channels and we send messages. It sort of looks like the PyCalculus, the formalism that we've seen so far, right? So what's that? A ping pong. Okay, so that's our ping pong example from the beginning of this presentation. It's sort of formalized using PyCalculus. So now let's see if we can actually, before we write any interpreter, let's just see if it's actually doable just to write using this new API, write our new program using that new API. So here in master, I create a new channel that gives me a send port and receive port. I spawn 2 new processes where I passed those send channel and receive channel. And then I just have to wait on the receive channel. I just have to wait for message done. And I will know it's only that done, and I will not be able to send anything else. And ping and pong are pretty straightforward. I send a message ping on that channel. I'm expecting a message pong on that channel, and then I send on the same channel message done, and pong will be equivalent. So just wait for a message ping on this channel and then send pong back. It's easier to reason about. There are no PIDs, there are no IDs of processes. We just exchange channels, send messages, and all good. Unfortunately, this will not work. And there are reasons why it will not work, and the reasons are just complexity and nobody want to do it. So the problem is we can send channels to other processes. And when we get that channel, we can send message on that channel, that's fine, but we cannot receive new messages from this channel. It's blocked. And that's why they actually don't have a type channel. They distinguish between receive port and send port. And there's a quote here why they explain that how it's like super complex to do it. This is on the documentation from Cloud Haskell, from the distributed process. I've also had a conversation with Ronald Kuhn, who implemented typed akka, and he said like for him that adding this functionality would mean implementing the consensus protocol on top of that. Why? I don't know. This is what he said. I'm just repeating his words. But he's basically both akka type and Cloud Haskell. They just not allow you to do anything like that. So I'm sorry, it's not doable. So if we had a conversation with Thomas yesterday that he actually tried to write the interpreter for PyCalculus using Cloud Haskell, and I said like I've been there. It's unfortunately undoable. So the issues with PyCalculus itself is that it's synchronous by nature. We have this dilemmas with implementation, and there's also the problem of notion of what actually name is. So let's try to right now reason about synchronicity. Obviously, if somebody created a paper about synchronous calculus, somebody else had to create a synchronous one, and so it did. The paper that I've read uses this concept of chemical state machine. The idea is like in chemical state machines, you have some abstractions which they can either froze and they just how you say merge together, and if you heat that machine, they can actually divide back. And they use that concept in that paper extensively. It's a nice thing to reason about. I'm just saying it adds, I think, a little bit too much complexity just to reason about one thing. So what I'm going to show you is not exactly how the syntax of asynchronous PyCalculus looks like, but I will just explain the idea in one slide instead of 15. So while in synchronous PyCalculus, when we were sending a message, we were synchronously waiting for for the message to arrive, and then we can continue with our continuation P. In asynchronous PyCalculus, this P just disappears, and that's it. There's no way to do it, and done. So, as I said, it's powerful enough right now to reason about asynchronous calculation, and they also showed that it's even you can go from asynchronous PyCalculus to synchronous one. You just cannot go to the other way around. So synchronous PyCalculus is more powerful than asynchronous one. But given I have 15 minutes, which is like crazy, I will try to talk about raw calculus. So the raw calculus expands on the idea of asynchronous PyCalculus, and in our chain, the language that we use for smart contracts is called RHO-lang, and RHO-lang is like raw calculus plus, I would say. I might be lying, but that's how I basically see it. Like it's a little nicer syntax. Have some extensions for security reasons, but other than that, it's pretty much the same. The problem with PyCalculus and asynchronous PyCalculus is that even though the theory talks about processes and channels and names and how we can send names over channels, they don't really. It's not really closed theory because we don't know what names and channels are. There are some abstractions. They are the exercise for the reader. They are implementation details, so they vary between the implementations. It's something that you decide what it is depending on how you implement your system. Raw calculus tries to close that theory, so that only we get a syntax that we can reason about processes, how we construct processes. We also get a syntax where we can reason about names, how we construct names. And names are sort of like quoted processes. The best way to think about quoting a process is thinking in terms of Lisp. As you all know, Lisp, even though it's a functional program, it doesn't even have higher order functions, right? What it has is S expression and M expressions. So two different languages. One language is responsible for constructing data, and the other one is responsible for calculations. However, they have this concept of lifting or quoting and also dropping. So you can take a structure, or so you can take a calculation and lift it into structure, and then you can also go back. And that's how they have higher order functions. They just take a function, lift it to structure, send it over to somebody else, and then he will just drop it and have a calculation back. So that concept is being used in raw calculus. And sorry, my allergies are back. Not only we have a syntax to create processes, but we also have a syntax to create names. And there's basically one construct that we use. It's called quote. So given that I have a process, I can create a name by just quoting that process. Okay, that's what it is, nothing else. We can obviously have processes which will run in parallel. We can have something which is called a lift operator. So what a lift really is, it takes your process P, packaged up to a name, so like quoted P, and that becomes immediately available on the output X. That's all it is. It just takes your process, lifts it into a value, and makes it available on X. And so that it tends along of like similar to ni-X in previous calculuses. The other one is called drop. So given that I have some name X, I can just drop it. I can bring back the process that was just lifted before. So here previously I could lifted my process to a name X, and operator drop will give me a process back. It's important that this process is. I have it. Wait. We will see this in example, but this is sort of like it awaits for somebody to substitute it even further. But we will see that in examples, hopefully. Now, before we move further. This little thing, like sending a message Y over channel X, doesn't exist in the syntax itself, but is a syntactic sugar. It's equivalent to this. Now, given limited time, it might look weird, but I have actually a proof at the end of the slides why that is. So just for now, let's keep it in our mind that whenever we see send message Y over X, it's equivalent to this structure from the syntax that we have. We have ability also to wait for messages, and we have a zero process as well. So another question would be, how can I create a simple name, the first name in that system? Any ideas? With what I have. This is the only way to construct a name, right?
You could quote the inner process.
I could quote 0. And I have a name. I could use the output constructor to use it to create. So this sort of so just you guys see. I just want to say send X over X, which is that part, which at the end I just have to quote it, and I can use the input one as well. Now we also have run things in parallel, right? So maybe we could do things like that. But now the question is, are those equivalent? The intuition tells us if that process is behaves the same, the name should be equivalent, right? It should be the same name. So those three X, Q, and P, the intuition is telling us that they should actually be the same name. So as it turns out, one of the things that you get from reasoning, like one of the benefits from the raw calculus, it actually spawned a discussion about what's the power behind actually reasoning about what names are. Because let's think about it. In order to reason whether the processes are equivalent, so here are some structured concurrents. Those are pretty much the things that we've seen so far in previous calculus. Also, that Wikipedia one is actually stated here, so it's explicitly said that P in parallel to 0 is just P. Now, in order to reason whether I have like this only applies if I still need to have ability to say whether P and Q are the same thing or they are different. Now, I can reason about it with alpha equivalence. So here, those two are equivalent, where we just like exchange V for Z. But other than that, they are equivalent. But to make that substitution here, I have to reason about whether Z, V, X, Y are equivalent. So in order to talk about equivalence of processes, now I have to talk about what it means that names are equivalent. Fortunately, we have a definition of what it means that the names are equivalent. So the first one is, if I quote and I drop X, I get X back. That is pretty straightforward, hopefully. But also, what I have is that if process is structurally equivalent to P process P is structurally equivalent to process Q, then messages built on top of those processes are also equivalent. But if you haven't fell asleep so far, you might be thinking, wait, what? It's like a chicken and an egg problem, or ACDC. If you made them and they made you. Because in order to reason about equivalence of process, I have to now have have ability to reason about the equivalence of names. In order to talk about equivalence of names, I have to reason about equivalence of processes. It's a never-ending story. It's a loop. Fortunately, unfortunately, and honestly, don't have time for it. But this paper about raw calculus is the best academic paper I've ever read, because first of all, there are jokes in it. I can understand it. And there are even emojis being used in it. So the best paper to actually read, and if you're interested, while that isn't a problem, it is within that paper, it's strictly reasonable and comprehensible. I can give you an intuition. Yes, they are sort of depending on each other, but if you look through on the examples, they diverged towards a process zero. You start with a process, you need an equivalence of name, then that needs the name equivalence of a process, and so on and so forth. But it doesn't expand to eternity. It just diverges towards at some point a result. So that isn't an issue, fortunately. And now the same way that we have reductions on pi calculus and asynchronous pi calculus, we have operation semantics for RHO-lang as well. So what it means here is that if x0 and xy, so names, are equivalent, and then we have some process Q which was quoted and made available on x0, and we have some process here that waits for message y on xy, and remember those two are equivalent, then it means that you can just continue with P, where you exchange every occurrence of y with quoted x. It's equivalent to that communication reduction that we had. Was that? Quoted Q. Quoted Q, sorry. It's equivalent to that reduction that we had previously in other calculuses. And there's also an equivalent that if P reduces to P prime and P is in parallel to Q, it will still reduce regardless whether it is running in parallel. And exactly the same equivalent that we've seen before. So if P is structurally equivalent to P prime, and so is Q to Q prime, and Q prime reduces to P prime, then P will reduces to Q. And now we have, well, I'm actually on time. So now we have ability to, I told you that this little syntactic sugar is equivalent to that, and now we can actually prove it. So if I have a message that I send Z on channel X, and on the same channel X somebody else would try to return a message, sorry, a message Y, what we are hope to get at the very end is this, right? That message Z will be sent here, and it will be just exchanged for all the Y's within P. This is what we try to sorry, get to. So as I said, this is just synthetic sugar to this, so I can expand this synthetic sugar to the sugar version of it. Then, given the rules, the reduction rules that we've seen here, basically that communication rule, we can actually see that is equivalent to having a P where we send where we send a message which is a drop of a lift, where we also seen in the name equivalent like 20 slides ago that this is just Z, right? And we can just reduce that to Z. And that sort of proves the point. RHO-lang, as I said, is probably Mike sitting here. I didn't realize till just now. RHO-lang is sort of like, as I said, for me it's basically a raw calculus plus. One of the things, like if you are on the blockchain and everything is available to everybody else, you might have a problem that you don't have a knee operator, or you don't have an ability to say that I want to have my private channel X, right? So that's like, for example, we bring back that knee operator just so we have an enforceable name, so I can communicate with somebody else and have assurance that nobody else will listen to it. Because without it, in raw calculus, I can create my little name out of some processes, but then somebody else might just create it as well and just start listening to the messages that I sent to somebody else. But it's pretty much really easy if you understand raw calculus to start working with RHO-lang itself. And it's, as I said, being used in this project. The topics we didn't cover is by simulation, for which I would need like probably another 20 or 25 minutes. And those are all the papers that I've read to understand that topic. I've joined the company in February. I had like 1 week to get on track, so this is all I had to read in 1 week, which was fun. And yeah, my name is Szulc. This is my Twitter, and remember, we are hiring, and that's all. Thank you very much.